Advancements in AI research are transforming creative tasks in filmmaking and post-production. Some of these advancements include digital face replacement, character style transfer, and many more. And the expectations and capabilities in this field are rapidly evolving due to the development of new AI tools. This increases the need for collaboration between AI researchers and filmmakers. There are existing capture setups that aim to foster AI research in this direction, such as the Mixed Reality Studio developed by Microsoft or the Relatables by Google. The problem with these capture studios are the fact that they use complex and sophisticated capture systems, which are tailored mostly for research, from RGBD camera rigs to complex lighting and many other things that filmmakers would almost never use in practice. Another problem is flexibility. These systems are mostly designed to be static, and this restricts filmmakers from exploring creativity outside of a confined space. This makes the research and technologies mostly driven by technical experts instead of the filmmakers or creative professionals who are the end users. The goal of this thesis is to design a studio setup that allows creatives to perform their creative task while also allowing research to be done simultaneously. To achieve this, first we use equipment filmmakers are familiar with to allow them to drive the production, while also allowing our research goals to be achieved. Secondly, we carefully select this equipment in a way that they are easy to use by both technical and non-technical experts, and flexible enough to be used outside of a studio setting. By designing our studio this way, we aim to create a collaborative environment where the research is driven by the needs of the creatives. This presentation is divided into three sections. We'll start with the studio setup and discuss our selection of the equipment, including choice of green screen, cameras, lenses, lighting, and other studio equipment. Then we'll go to the capture and data processing, where we focus on time synchronization and camera calibration, which are critical aspects of our studio research pipeline. We will also discuss certain capture procedures, which we put in place to ease these processes. Finally, we will talk about our green screen keying method and discuss how we accurately remove the green background from the recorded videos in our studio, so we can replace it later or use it for further computational photography research. I'll start with the studio setup. A very crucial part of our studio is the green screen, which is commonly used in the movie industry. Green screens are used to facilitate a process called chroma keying. Chroma keying involves digitally removing a specific color from a scene, allowing for the background to be replaced with another image or video. When setting up our studio, we had the option to choose between the traditional bright green or the dark green screen. The traditional bright green screen provides a strong signal that is easily distinguishable from most subjects to be keyed due to its high saturation and brightness. But it is subject to color spill, where the green color reflects on the subject. This can create artifacts in the keyed image. The dark green screen, on the other hand, while it does not provide strong signals compared to a traditional green screen, the effect of color spill is minimal. We opted for the dark green screen in our studio since we aim to utilize neural networks for the keying process, which differs from standard traditional chroma keying. Another issue we faced when setting up the green screen is shadows, as shadows on the green screen can cause inconsistencies in the color, which is problematic for our green screen keying method. To reduce the shadow effect on the green screen, we position two light sources at equal distance from the green screen and angled similarly. This ensures uniform illumination for both angles, and any shadow cast will fall off to the sides, out of the main camera's view. To summarize the equipment we used in our studio, we chose to use a mirrorless camera because of its compactness and portability, while also providing high quality videos. We utilized a variety of lenses with different focal lengths. We used the 100mm lens for close-up shots like the Legos. We used the 50mm portrait lens for presentations and lecture videos. And we used the 15mm lens for 2 or more persons, such as interviews, as they cover wide angles. For our audio devices, we also utilized external microphones for better audio quality. We use the shotgun microphones because they are effective at isolating sound from a specific direction, and we also have the wireless microphones, which are perfect for capturing audio from presenters or actors without the constraints of wired connections. Lastly, we utilize a compact and portable timecode generator. This device is used for synchronizing all the cameras in our setup, which is useful for both post-production and multi-camera analysis. Now that we have our studio components set up, in the next section, we will discuss two critical aspects of the data capture and processing pipeline of our studio, which are time synchronization and camera calibration. A bottleneck we discovered was that even after synchronizing with the timecode generator, we noticed some shifts between camera frames, as you can see in this image. We further analyzed the audio waveforms using clap signals and noticed that for the same sound signal, we can see about 30 milliseconds shift between cameras. This discrepancy is known as phase shift in cameras and is due to slight variations in each camera's digital shutter. What this means is that although they are synchronized to the same timecode, the actual start time of frame capture can vary slightly across cameras. In order to obtain the accurate time shift between cameras, we use a clapboard to mark the audio signals. This then allows us to compute the cross-correlation between camera audio segments to find the shift. To improve the accuracy, we compute the cross-correlation across all clap audio segments. Achieving millisecond synchronization is challenging due to the missing frames, and this requires further research. Consequently, we store the delay information for future synchronization improvements. The next critical part of our pipeline is camera calibration. Camera calibration is the process of estimating the parameters of a camera to accurately map the 3D world to a 2D image. The extrinsic parameter is the transformation from world coordinate system to the camera coordinate system, and the intrinsics is the transformation from the camera coordinate system to points on the 2D image plane. Together, these parameters transform 3D world points to 2D image points. If you look at the mathematical representation of the transformation from worlds to image points, where uppercase X represents the homogeneous coordinates of a 3D point in the world, and lowercase x denotes the corresponding 2D point in the image. P is the transformation matrix that consists of the intrinsic and extrinsic parameters. The goal of camera calibration is to estimate these parameters that make up the intrinsic and extrinsic matrix, where fx and fy are the effective focal lengths in the x and y directions, cx and cy are the x and y coordinates of the principal points in the image. R is a 3x3 rotation matrix that describes the orientation of the camera relative to the world coordinate. T is a 3x1 translation vector that describes the camera's position relative to the world's coordinate. The calibration process in our studio involves capturing images of a checkerboard pattern from multiple camera angles. We utilize 3 checkerboard calibration patterns of different dimensions. The larger pattern offers more points for the calibration process, enhancing the accuracy of the camera parameters. The smaller pattern is easier to manage in tighter spaces, or when a close-range capture is needed. We also have the medium pattern, which is in between. This variety ensures flexibility in different recording scenarios. The first step of the calibration process is the checkerboard point detection. Since our images are 4K resolution, to avoid long computation time, we propose to estimate a rough corner location in a multi-scale manner first. In case no matching pattern was found, we increase the resolution by a factor of 2 and rerun this process. We continue this process until half of the original image resolution. If no corners are found at this resolution, we discard the image from the calibration sequence. Finally, to extend to high resolution, we perform sub-pixel refinements using the scaled-up version of the detected points. To obtain the intrinsic parameters of each individual cameras, we achieve this by minimizing the reprojection error between the 2D points and the reprojected 3D points, where K is the intrinsic parameters, R and T are the rotation and translation vectors of the detected patterns of that specific camera, and D is the distortion coefficient. We obtain the extrinsic parameters of each camera by estimating their pose with respect to a reference global coordinate. For this, it is crucial that cameras are not only synchronized such that they capture images of the pattern at the same time, but also maintain a fair horizontal distance with their neighboring cameras, such that they are overlapping views. For example, if you have a calibration system consisting of 2 cameras, camera 1 and camera 2. We assume that camera 1 sees pattern 1 and pattern 2, and camera 2 sees pattern 2 and pattern 3. In order for us to transform camera 1 from camera 1's coordinate space to camera 2's coordinate space, since they both have pattern 2 as overlapping patterns, we can use these patterns to transform camera 1 from camera 1's coordinate system to camera 2's coordinate system. And then since we have camera 1 in camera 2's coordinate system and camera 1 saw pattern 1, we can transform pattern 1 to pattern 2's coordinate system. We repeat this process for all the cameras in our calibration system to transform each camera from their own coordinate system to a reference global coordinate system. Finally, we then use module adjustment to optimize the camera parameters by minimizing the sum of all reprojection errors, where P is the pose of all the cameras in the system. One issue we discovered was that sometimes the medium pattern struggles to create overlapping pattern views, as the pattern was unable to fit into the frame. This issue is problematic because it can lead to a disconnected camera system and also reduce the number of detected patterns. To mitigate this, we modified the conventional calibration method, which involves calibrating using a single pattern to further allow for a combination of different patterns. This way, we can then calibrate using the medium and smaller pattern together. We performed our analysis to see the effect of this by performing calibration using the medium pattern only, the smaller pattern only, and the combination of both. The combination of both detects way more patterns, which reduces the chances of a disconnected system. Our primary objective is to avoid losing any camera from the system, recognizing that the trade-off would be a slight increase in the overall reprojection error. We record our subject in front of a green screen so we can remove it during post-production. In this section, we'll discuss our method for an automatic and effective green screen keying pipeline. We designed this pipeline in a way that it is flexible to different user inputs to ease the keying process. The reason we're able to separate the foreground and the background is because of what we call an alpha matte. An alpha matte is a grayscale image that represents the transparency or opacity of the foreground in an image, where the white region is referred to as fully opaque and alpha is 1. We also have the fully transparent region, which is the background, where alpha is 0. And then there's the semi-transparent region, where the alpha is between 0 and 1. This region is the transition region between the foreground and the background. Green screen keying is part of the more generalized problem in computer vision called image matting, where an image is defined by the compositing equation. Given a composite image, image matting aims to recover the alpha and foreground colors, so we can replace the background in the image. Image matting is a highly under-constrained problem in the sense that the only information we have is the composite image, and this means we have 7 unknowns, which are from the foreground colors, the background colors, and the alpha matte. Given an image, some methods try to simplify the matting process by providing what we call a trimap as input. A trimap is a labeled grayscale image that divides the pixels into 3 regions, which are the definite foreground, the definite background, and an unknown area. The goal of the trimap is to ease the matting algorithm to focus on the unknown area using information from the known foreground colors and background colors. Some methods also add a clean plate, which is a picture of the background just before the subject comes in frame. The aim is to reduce the number of unknowns to just the foreground and alpha. It is also important to note that the clean plate is only ideal when the cameras are still, and this is the case for our studio setup. To give an overview of our pipeline, we start with stage 1, which is the trimap generation network. This network estimates the trimap, which should be useful to ease the matting process. In stage 2, we have the image matting network that utilizes the trimap output of the first stage and estimates the alpha and foreground colors. Finally, we have the third stage, which is the video matting network. This network takes as input the estimated alpha and foreground colors from the image matting network to estimate the next frame's alpha and foreground for videos. We design our pipeline in a way that is very flexible to different use cases. For instance, if the user has a hand-drawn or more accurate trimap, we can ignore the first stage and move to the second stage. Also, if the user has an initial alpha and foreground estimates for videos, we can ignore stage 2 and move to the third stage. We'll start with the trimap generation network, which helps to reduce the matching process. We simplify the trimap estimation task by providing the clean plate alongside the image as input to the network. This is because the clean plate helps the network distinguish the foreground from the background. But for some camera views in our studio, the scene has distracting objects, making it challenging to identify the foreground. This led us to add an additional input to the trimap estimation network, which is a mask that allows us to specify where the foreground should be. We formulate the trimap estimation as a classification problem. The goal is to estimate the foreground and background mask, which can be combined to create a trimap. We utilize the binary cross entropy loss. We also add an additional MSc loss for unacceptable cases. These unacceptable cases include predicting unknown as foreground or background, or predicting foreground as background, or background as foreground. These unacceptable cases are very crucial for the matching network in the next stage, because the matching accuracy is only as good as the trimap input. Stage 2 of our KIM process is the matching network, which involves estimating the alpha and the foreground from a composite image. If you notice, we have an additional network, which is the background in painting network, which takes in the image, the trimap, and estimates a background, which is used as an input to the matching network. You may be wondering, why didn't we just use the clean plate? We'll talk about that in this section. Like we've discussed before, to ease the constraints of the matching equation when estimating the alpha and foreground, we provide a clean plate to represent the background. But these clean plates often have some discrepancies compared to the true background, such as the issue of shadows we spoke about when we illuminated the green screen. We also have some objects which are in the image but not in the clean plate. For instance, the chair, the laptop, and the red chain. This makes the clean plate unusable for our matching task. We follow the background in painting method from Tang et al. In 2019, where they mentioned that this is similar to the image in painting problem but simpler. In this case, we replace the mask input of the general in painting method with our trimap because we only care about in painting the unknown region in the trimap. We utilize a state-of-the-art image in painting network, which is referred to as LAMAL, and modify the losses to compute on only the non-foreground regions. Now that we have been able to estimate the background, we can move to our image matching network. Our image matching stage conceptually follows Levin et al. From 2008 based on local affinities. They show that for a spatially constrained image window, the matching problem can be solved via closed form optimization, subject to some smoothness constraints. This smoothness constraint is based on the assumption that within a small local window, the foreground and background colors should vary smoothly, leading to a smooth transition in the alpha values. This constraint enforces that the alpha values of neighboring pixels should not change abruptly unless there is a significant color difference, indicating a boundary between the foreground and background. One of the issues with this method is that they apply the smoothness prior uniformly across the image, which can be too restrictive or too loose, depending on the content of the image. Given these limitations, we lift this approach by replacing the closed form optimization with a convolutional neural network architecture and estimating both alpha and the foreground colors. The advantage of using this architecture is that it incorporates the local smoothness prior through its lens filters. These filters can adapt based on the specific content of the image, applying stronger or weaker smoothing where needed. For the losses, we utilize the mean absolute error on both the predicted alpha and the predicted foreground. We also have an additional multi-scale gradient loss on both the predicted alpha and predicted foreground, which ensures accurate prediction of the edge and fine details at multiple scales. For the predicted alpha, we add a hard mining loss, which focuses supervision on the pixels that are hardest to determine, as identified by the highest absolute differences. For the foreground colors, we utilize a color loss in the YUV space. This is because individual RGB losses do not measure output color, and YUV represents the images in terms of brightness and color. This can be more perceptually meaningful because it aligns more closely with how humans perceive images. Finally, we have the compositing loss on both the predicted alpha and predicted foreground. This loss enforces the accuracy of the reconstructed input frame by ensuring that the predicted foreground and alpha adhere to the compositing equation. Finally, we have the video matching network, which takes the previously estimated alpha and foreground to estimate the next frame's alpha and foreground. During training, we supervise the network in a cycle-consistent manner to simulate change in time. In the first pass, which we assume as time t, the network takes as inputs the previous foreground, previous alpha, and current image frame to predict the current foreground and current alpha. In the second pass, which we assume as t plus 1, we pass the predicted current foreground and predicted current alpha as well as the previous image frame to then predict the previous foreground and previous alpha. This way we can compute the loss on the change in the predicted current estimation and the predicted previous estimation. During data augmentation, we generate two types of tri-maps. We first generate the ground truth tri-map, which we use for supervising the tri-map network. The second type of tri-maps we generate during training are the dilated tri-maps to simulate user-drawn tri-maps for the inpainting and image matching network. Like I said, we want our network to be robust to different kinds of tri-maps, not only the ones generated by our tri-map network. These dilated variations of the tri-map make our network robust to different kinds of tri-map inputs. During training, we also modify the compositing equation to account for change in illumination between the clean plate background and the background after compositing. This makes our network robust to changes in illuminations or shadows between when the clean plate was taken and after the subject is in frame. Conceptually following the closed formatting approach, we want the patches that our network see to contain all three regions, which include the foreground, the background, and the unknown. This way, the network can propagate information from the known foreground and background colors to the unknown regions using the lens smoothness prior. So 95% of the time, the network should see all three regions, and 5% of the time, the network should see either full foreground or full background. We do this because during inference, it will be performing convolutions, and there will be cases where it sees either of just the two. For our experiments, we show that performing inference at a resolution twice the original input resolution leads to a substantial enhancement in matching quality. This has been validated by previous works by Miangole et al. From 2021 and Cariaga et al. From 2023. We also compare our method against state-of-the-art image matching methods such as background matching V2, FBA matching, and robust video matching. Our method excels in reconstructing fine details such as hair and glasses, which is critical for high-quality matching, especially in post-production environments. We also have the case of intense grain spill. This is a case where the tri-map is insufficient for keying. As you can see, the grain spill on the subject leads to the network confusing the spill on the foreground as a mix of both foreground and background at regions specified as unknown in the tri-map. Our method is robust to these cases because the background inpainting network propagates the known background to the uncertain region, effectively distinguishing the inferred background from the foreground mixed with the spill. To further validate our method, we conduct comparisons against commercial keying solutions, specifically keylight. Our method correctly handles scenario where keylight overcalls the grain, such as estimating inaccurate alpha mat for an earring that is green, an issue where keylight often fails. We also compare our image matching network and video matching network in terms of temporal coherence. As you can see from the result of both networks, you will notice that the video matching network keeps a consistent alpha over multiple frames compared to the image matching network. This is more noticeable at the glasses. We have successfully designed a flexible and user-friendly computational photography research studio. We have designed it in a way that both production and research are done simultaneously, using familiar production equipment. In this studio, we've been able to shoot production quality videos for research paper presentations and interviews. We've also been able to utilize this studio for research like multi-illumination analysis and shadow analysis. An important consideration when designing a studio is complete elimination of external light sources. Since we want a controlled lighting setup, It is important that we completely block all external light sources so it does not affect the illumination of the scene. We achieve this by using a matte aluminium sheet to block light from entering the studio. One limitation of our studio pipeline is that the use of a checkerboard pattern limits us to always have the pattern fully visible in frame before points can be detected. Even though we solve this by mixing patterns, this makes us capture up to 50 calibration orientations per camera, including using the smaller pattern to increase the chances for a fully visible pattern. Not only is this a long process, but it also shortens the lifespan of the clapboard due to so many claps. Another limitation is that while our video matching network maintains temporal coherence compared to the image matching network, we start to notice drift in accuracy from the 50th frame. To solve this, we run the image matching network again at the 50th frame and continue with the video matching network for the next 50 frames. In terms of future work, while we are able to obtain the milliseconds time shift between cameras, the complete synchronization is still left unsolved due to missing frames. An approach can be to interpolate frames to account for these discrepancies, but this approach requires further research, especially for high-quality frame interpolation. This research studio was funded by Canada Foundation for Innovation and BC Knowledge Development Funds under the project Computational Cinematography. Thank you.